Okay, so it's problem solution day. We're going to go start with exam 2, and then we'll do a few problems from the Rankine cycle homework. Okay, so number 1 from exam 2. So you have a piston cylinder, and it's water. And it says that it starts as a saturated liquid with a volume, an extensive volume of 0.1 cubic meters. And then it goes so volume is 0.1, pressure is 1 bar, and that pressure stays constant. Then it ends up with a volume 2 of 10 cubic meters. And we want to calculate the quality and the work. And so the quality suggests that this is, a mix at saturation. Okay, well, I gave you a table for water, and so you can look everything up, and one of the things you can look up is the specific volume. So we know that the specific volume at state 1 is 1.0432 times 10 to the minus third. And we know that, the specific volume is the extensive volume divided by the mass. So you can get the mass from that. And so the mass is 0.1 divided by 1.0432 times 10 to the minus third, and you get 95.86 kilograms. So now we have the mass, and now you can look up let's see, so now we know the mass, and we already knew the extensive volume at instant 2, state 2. So the specific volume is 10 divided by 95.86, which is 0.104. And now you can go, for part A, you can go 0.104 is equal to the quality times look up the specific volume for a saturated vapor, which is 1.694 plus 1 minus x of that other one, which is 1.0432 times 10 to the minus third. These are both just from the table. And you can calculate that the quality is 0.0608. And then for the second part, the work. Actually, a lot of people calculated the work by trying to set up like a first law equation, but there's heat transfer and you don't know what the heat transfer is, and so you really can't do it that way. I don't know, maybe half the people started that direction. What you got to do is you have everything you need to just calculate this integral. The pressure is constant.
Yeah, simply the work of expansion.
Right. So the pressure, so it's 1 times 10 to the 5th times 10 minus 0.1, and you get 990 times 10 to the 3rd joules. Okay, so that's the first one.
Right, thanks. I'm gonna go grab my notebook. I'm gonna my vehicle. Continue on without me.
Okay. And then the second one is air, and it's a compressor. And it's a steady state compressor, so we'll be able to simplify some stuff from that. The mass flow rate is 0.2 kilograms per second. The temperature at the inlet is 290 Kelvin. The temperature at the exit is 350 Kelvin. Heat transfer occurs at a rate of 1 kilowatts from the compressor to its surroundings. This was a sign error that a few people made. You have to, take that from the wording. If heat is going from the compressor, from the system to the surroundings, that means that Q dot is negative 1 times 10 to the 3rd. And we want to, we're going to ignore kinetic energy and potential energy effects, and we want to calculate the power output. Well, as soon as you see compressor, you know that this is going to be a control volume problem. And we can forget about the other stuff. And this goes away. So we have 0 is equal to negative 1 times 10 to the 3rd minus W dot. I guess I'll move W dot over to the other side. And then plus M dot was given, that's 0.2. And that's times the quantity HI minus HE. And so all we have to do is figure out the change in specific enthalpy. This is an ideal gas. It says to treat it as an ideal gas, so we know that the change in specific internal energy is CV times the change in temperature. And then the change in enthalpy is the change in specific internal energy plus R times the change in temperature. So this is CV plus R times delta T. And we're given that CV is 0.72 times 10 to the third, and R is 287. A few people had like a unit mismatch. They used 0.72 instead of 720. That I didn't take off a lot of points for that, but that does give you the wrong answer. Because that 0.718 is given in kilojoules. So if we're doing everything in SI units, you have to convert to joules. So this is really 718. So delta H is, what do you get if you add those? So 1005 times 290 minus 350. So you get negative 60,300. And then plug that into the equation we had, and you get W dot is equal to 1 times 10, negative 1 times 10 to the third, minus 0.2 times 60,300. I did it backwards. HI minus, so 290, 290 minus 350. So that's negative 60. I'm getting something different than I got before, but maybe this is right. I guess maybe I just have a sign error when I calculated it before. Let me just make sure here. Is the initial 290? The initial is 290, yeah. Isn't it like the final minus the initial? Well, we are just, time doesn't really matter. You're just calculating a difference in specific enthalpies. So it really could be either one. We're just, I'm treating
Since we're calculating the input, okay.
Yeah, so
Okay.
well, I think this is right. So negative 13,060. And that's in watts. Okay, I think that's right, yeah. I just had the wrong answer before. Okay, number 3, we have an ideal gas. We don't know what it is, but we can use all of the ideal gas equations. We know that whatever it is, it has an R value of 300 using SI units. There's 5 kilograms of it. We know that the starting pressure is 10 bar. And the starting temperature is 370 Kelvin. And it has a final pressure of 5 bar. It's isothermal, so this is a constant temperature, so T2 is also 370 Kelvin. And we want to first calculate the change in specific entropy. And then second, calculate the total heat transfer for this process. Well, we know that we can use this equation. So for part A, if you have a small temperature change for an ideal gas, the change in specific entropy is Cp times the natural log of T1 over T2 minus R times the natural log of P2 over P1. And this first term goes away because natural log of 1 is equal to 0. So you don't even have to know what that Cp is. So the change in specific entropy is 300 times natural log of, this is negative, sorry. Negative 300 times natural log of, 0.5 over 1. Or what was that? 5 over 10. Anyways, and for that you get 207.944, I guess, joules per kilogram Kelvin. And then for the second part, now we're trying to calculate the heat transfer. I didn't write this down, but it's internally reversible. And that's important. If you see internally reversible in a problem involving entropy, remember that what that means is the change in total entropy is equal to the total heat transfer divided by the temperature. Okay.
Across the boundary.
So, right. So that should be like, okay, you see the internally reversible, we're probably going in this direction. We've already calculated the change in specific entropy. We have the mass, so the change in extensive entropy is 5 times, delta little s, which is 207.944. And that's equal to the heat transfer divided by the temperature at the boundary, which is 370. And so you get that Q is 384 times 10 to the third joules. Does it make sense that heat goes into the system for this process? It makes sense if you think about it this way. So you're starting out with an ideal gas, and then you're letting it expand. And if you let an ideal gas expand and there's no heat transfer, the temperature is going to go down. But this is isothermal, the temperature stays the same. And so heat has to come into the system in order for that temperature to stay the same. And so that positive value of Q makes sense. And number 4, we've done a couple examples like this. There's a 1 kilogram of metal with a specific heat of 460, and it has an initial temperature of 1000 Kelvin. So that's really hot. And then we have 30 kilograms of liquid water. The C for that is 4186. And the initial temperature for the water is 280 Kelvin. And first, calculate the equilibrium temperature. Second, calculate the entropy production. And third, show that the reverse process couldn't happen. Well, we're assuming that these are incompressible. And so the change in specific internal energy is C times the change in temperature. And so the change in extensive internal energy is the mass times the specific heat times the change in temperature. And since this is an isolated system, the total change in internal energy has to be 0. So we have 1 times the specific heat of the metal times the change in temperature of the metal, which is the final temperature minus 1000. And then plus 30 times the specific heat of the water times the quantity T minus the initial temperature of the water. And that all has to be equal to 0. There's no change in internal energy for the whole system. Solve this and you get that T is 282.6 Kelvin. And now we want to calculate the entropy production. Well, we'll calculate the entropy, the change in entropy for each of these two things. And so the change in, I guess let's do specific entropy first of the metal. Is 460, the specific heat, times the natural log of the final temperature divided by the initial temperature. Sorry, this is the metal. So the final temperature divided by the initial temperature, which is 1,000. And for the water, it's the specific heat of the water times the natural log of the final temperature divided by the initial temperature. And then just multiply each of these by the mass. So the change in extensive entropy is 1, because there's 1 kilogram of the metal, times delta S for the metal, plus 30, because there's 30 kilograms of the water, times the change in specific entropy for the water. And you come up with a change in entropy of 579.41 joules per Kelvin. And then to show that it couldn't happen the other way, you know, what you'd be doing is flipping, taking the reciprocals of the things inside the natural log, and you would get that the change in extensive entropy was negative 579. And that's not possible. Any questions about that? Okay. So the next thing, so let's go on to the homework problems. For the Rankine power cycle. And I think the questions that I kind of had 2 similar questions for each kind of type of thing that we talked about. So I'm just going to do the odd problems 1, 3, and 5. We haven't done past 5 yet. Notice that I've corrected it now, but it was wrong when I assigned this problem. On number 5, you have to know to do this problem that when the water enters the turbine, it's a superheated vapor with a pressure of 10 megapascals. That's what was given before, but you also have to know the temperature. You can't do this problem. And the temperature is 480 degrees Celsius. Okay, so let's start with number one. So it's a Rankine cycle. The working fluid is water. There's one problem. I think there's only one problem in this whole thing where there's a different working fluid, and it's the refrigerant that we have a table for. Everything else is water. This is an ideal Rankine cycle. So that means that, well, I'll draw the temperature entropy diagram, but we know the states of the, we know the phases of the water in the different states. And we also know that the pump and the turbine are both isentropic processes. So we know that the entropy stays the same as the thing goes through the pump and goes through the turbine. So I'm going to set this up. So here are my states. So state 1, state 2, 3, and 4. And I'm just going to sort of write down what we know. 1 to 2 is the turbine. And that is isentropic. 2 to 3 is the condenser, and that's isobaric. 3 to 4 is the pump, and that's isentropic again. And then 4 back to 1 is the boiler, and that's isobaric again, constant pressure. And I didn't even write down what this problem is asking for, but really on all of these problems, you're just trying to come up with the enthalpies for the different states. If you can come up with the enthalpies for all 4 of these states, then you can answer any question it asks you. So let's see. Saturated vapor enters the turbine. So at state 1, we know that this is a saturated vapor. The pressure P1 is 10 megapascals. The condenser pressure, okay, so what do we have at the beginning and end of the condenser process? I didn't draw the diagram, but let's draw it. Okay, so here's state 1. Here's state 2. Here's state 3, 4. And then there's that 2-leg process going from 4 to 1 through the boiler. Okay, so state 1, it's a saturated vapor. State 2, it's a saturated mixture of vapor and liquid. And we know that the pressure P2, that's given, and it's 6 kilopascals. At state 3, it's a saturated liquid. And the pressure is the same as it was at state 2. So P3 is 6 kilopascals. And then state 4, it's a compressed liquid. We know that the pressure is the same as at state 1 because the pressure is constant through the boiler. So P4 is 10 megapascals. Okay, so where can we look stuff up? This is water, so we have tables for it. Well, we can use the tables right away to find the enthalpies at state 1 and state 3. So, because, you know, a saturated vapor and a saturated liquid, all you need is the pressure, and we have the pressure. So we can just look those right up. And if you look them up, you get H1 is 2724.7 times 10 to the third. And state 3, H3 is 151.53 times 10 to the third. There is one other thing that we're going to need. So in dealing with the pump, remember, for this, we can treat this as an incompressible liquid. It's a liquid the whole time. And we can use that simplified form to calculate the change in enthalpy. So that one is easy. This one, though, and this is always the case for the ideal Rankine cycle problems, there's a mixture at state 2. And so we need to know what the quality is. So how do you come up with the quality? Well, from state 1, we can look up the specific entropy. So just look that up. It's 5.6141 times 10 to the third. And since the process from state 1 to state 2 is isentropic, that's also the specific entropy at state 2. So what we can do is look up the saturated liquid entropy, look up the saturated vapor entropy, and use our known specific entropy to find the quality. Okay, that's always the approach for these. Okay, so we got that. So let's go to state 2. And what we know is that 5.6141 times 10 to the third is equal to the quality times what we look up in the table for the saturated vapor specific entropy at that pressure. and that is 8.3304 times 10 to the third, plus the quantity 1 minus x times the specific entropy for a saturated liquid at that pressure, which is 0.5210 times 10 to the third. Solve for x, and x is equal to 0.652. And now we're going to just use x to find H2. So H2 is equal to 0.652 times the specific enthalpy for a saturated vapor, 2567.4 times 10 to the third, plus 1 minus this, which is 0.348 times the specific enthalpy for a saturated liquid at that pressure, which is 151.53 times 10 to the third. And you get that H2 is 1.727 times 10 to the sixth, or I'm going to write it the same way as I'm writing all the other ones. 1727 times 10 to the third. Okay, so this gives us our H2. And now the only one we have left is H4. Let me get this in your notes too. So this and this and this and this are just all table. Since we know it's state 2, it's a saturated mixture, we can, and we have the pressure, we can already look up the saturated vapor and saturated liquid values of any properties we want. The only thing we have to figure out in order to get H2 is we have to figure out that quality. So use the entropy for that. So now we just need H4. And we know that, so remember that for the pump, the rate of work per the rate of mass flow is equal to H4 minus H3. And we can also calculate this as the specific volume at 3 times the quantity P4 minus P3. And we have all that stuff. So H4 is equal to H3 plus V3 times the quantity P4 minus P3. Well, you could look up, I usually just, for the specific volume of liquid water, I just use 0.001. But you can go to the saturation table and figure out at that pressure, this pressure is 10 megapascals. look up the temperature, the saturation temperature at that pressure, and then use that to find the specific volume, and it would be about 0.001, but something slightly different. So H4 is 151.53 times 10 to the third plus 9994, and so it's equal to 161.5 times 10 to the third. And now we're finally done. We have the enthalpies for everything. I haven't even looked at what the question is asking us for yet. I just calculated the enthalpies, and then once you have those, everything's easy.
And one other thing for state flows too.
Yeah.
I mean, I know I can calculate it this way, but can we also do it the same way that we got state 2? By then just using the entropy and the pressure to...
Yes, you could do that. But it's sort of a pain because you probably have to interpolate. That's right.
Okay. Yeah, so this is just easier.
Right. But yeah, conceptually, that's exactly right.
Okay.
Okay, so what's it asking for? Determine the heat transfer rate and calculate the thermal efficiency. So first, let's do the one at the turbine. So QT dot over M dot is so that's going to be H2 minus H1. Right. Oh, I'm thinking of yeah, this isn't the turbine, I'm sorry. If we're doing heat transfers, we're doing the boiler and the condenser. So the boiler, it's going to be, so H1 minus H4. And we have those values, so, once we have those, just plug this stuff in, and you get 2563.2 times 10 to the third. And that's joules per kilogram. Then B, now we're trying to find Q dot of the condenser divided by M dot. The condenser is from state 2 to state 3. So this is going to be H2 minus H3. Plug in those values and you get 1575.47 times 10 to the third joules per kilogram. Based on these, what's the net power production? How would you calculate that?
Oh yeah, the net power is the heat at the boiler minus the QC.
That's right, because the only places energy goes, energy comes in at the boiler, goes out at the condenser, comes in at the pump, and goes out at the turbine.
Yeah.
And so, so it's just, so if you're trying to calculate W dot at the turbine minus W dot at the pump, it's just subtraction of these that gives you that amount. And then the last thing is just the total efficiency. This is equal to 1 minus the quantity H2 minus H3 over the quantity H1 minus H4. Plug in those values and you get 0.385. And now number 3, this is water again. It's an ideal Rankine cycle again. I'm going to do this first this time. So here's the temperature entropy diagram. There's state 1, 2, 3, 4. And we're given this time a mass flow rate. So m dot is 120 kilograms per second. And I'm just going to fill out these states again. 1, 2, 3, 4. And remember that 1 to 2 is the isentropic turbine. 2 to 3 is the isobaric condenser. 3 to 4 is the isentropic pump. And then 4 to 1 is another isobaric boiler. And from this diagram, you can see that at state 1, we are at a saturated vapor. At state 2, we're at a saturated mix. At state 3, we're at a saturated liquid. And at state 4, we're at a compressed liquid. And now we can start filling out the stuff that it gave us. It enters the turbine at 16 megapascals, so P1 is 16 megapascals. Since the boiler is isobaric, that means that P4 is also 16 megapascals. The condenser pressure is 8 kilopascals, so P2 is 8 kPa, and that's also P3. So you can fill out those, if you're given 2 pressures, you can fill out the other 2 because of the isobaric processes. And now it's all the exact same stuff again. We're trying to get the specific enthalpies. We can use the table already at state 1 and state 3. At state 1, the saturated vapor H1 is 2580.6 times 10 to the third. And then I'm also going to look up the specific entropy, At state 1, that's 5.2455 times 10 to the third. We don't really care about that, so why do I want to look up the specific entropy at state 1?
Or mixed vapor liquid.
That's right, because we're going to have to calculate that quality. So since this is isentropic, we know that S2 is also this, and then based on that, we'll be able to calculate that quality. At state 3, we can look up H3. (1316.6 times 10 to the third). And now at state 2, we know that 5.2455 is equal to X times the saturated vapor specific entropy, so 5.7432 times 10 to the third, plus the quantity 1 minus X times the specific entropy for a saturated liquid, 3.2068 times 10 to the third. These are both just looked up in the table. Solve for X, and you get that the quality is 0.804. And so based on that, you can get H2. So H2 is 0.804 times 2758 times 10 to the third plus 0.196 times the quantity 1316.6 times 10 to the third. And you get 2475.5 times 10 to the third. And now that goes there. And now the only thing that we don't know is the specific enthalpy at state 4. We're going to use, so state 4. So H4 minus H3 is specific volume at state 3 times the quantity P4 minus P3. So that's 0.001 times the quantity 16 times 10 to the 6 minus 8 times 10 to the 8 kilopascals.
Yeah, I was looking at that, so I got something different.
What did you?
I got the table out right
now.
now.
Yeah, okay, so from state 2, I think I used 8 megapascals. So
okay, that would make sense because I was like, what the heck?
Yeah, so can you tell me what you got and we'll calculate that?
Yeah. That one I got, it was 8.2287, that's for the saturated vapor.
For the entropy?
Yeah, for the entropy of the saturated vapor at 8 kilopascals.
Okay, 8.2287.
87,
okay.
And then for the saturated liquid, I got 0.5926.
Okay.
Which then for the quality, I got 0.6093.
Okay, 609. Okay, and so 609 And then this one is going to be 0.391. And what are the, what's the specific enthalpy for the vapor?
Oh, yeah, I have. That's the wrong page. I was like, wait a second. Then for the vapor, specific enthalpy would be 2577.
Okay. And then
For the saturated liquid, it's a 173.88.
Okay. And then what did you get for the?
For H2, I got 1638.2.
Okay.
Yeah, and then the e to the third.
Yep. Okay. So, and then, so we're down here now calculating H4 minus H3. Here's where I noticed I'd written it down wrong. So this should be 8 times 10 to the third. I have it as 8 times 10 to the 6th. And so H4 is equal to H3. So 1316.6 times 10 to the third plus 0.001 times the quantity 16 times 10 to the sixth minus 8 times 10 to the third. And what do you get for that?
I'll make sure I wrote that all correctly. Wait, that's for state 4?
Yeah.
I might have done that wrong.
So for this, I get one.
Oh, I think I see. Didn't we skip state 3? Because what we calculated prior to that was state 4.
For
state 4 is H. We wanted the H3 value, and you're using the H, right?
We're trying to calculate H4. We already looked up H3 because that's a saturated liquid.
Yeah, which I thought H3 was 173.88.
Oh,
yeah, you're still using 8 megapascals, aren't you? For that value?
Yes. So what did you get for H3?
H3, I had 173.88.
173.88. Okay. Okay. Minus. So did you get, so H4, did you just get like 15,000, 16,000? 15.99 times 10 to the third?
So I actually got 189.87.
Okay. Yeah, that can't be right. 189.87?
Yeah.
Times 10 to the third. Okay. And then that goes here. That's funny. So, I was doing it with these very small, with the condenser pressure only half as big as the boiler pressure.
Yeah,
and so I got this horrible efficiency and stuff. I'm like, oh, that's weird.
That's what I was about to ask him, so was your efficiency super low then?
Yeah. Okay, but anyways, now we went through the same exact steps as last time, got the same 4 enthalpies, and now it asks us roughly the same questions with some differences. We were given this time we were given the mass flow rate, So we can calculate actually W dots and Q dots instead of as ratios with the mass flow rates. But so the net power developed is W dot at the turbine minus W dot at the pump. And that is the mass flow rate times the quantity H1 minus H2 minus the quantity H4 minus H3. Plug those in and you get 1.1. Oh, no, because I'm plugging in the wrong stuff. So
Yeah, I got 111,169 kilowatts.
111 what?
And then 169.
169.
Yeah, kilowatts.
Okay. And then the heat at the boiler. So that's 120 times the quantity H1 minus H4. And what did you get for that?
For that, I got 286,884 kilowatts.
Okay. And then the efficiency. So that's 1 minus the quantity H2 minus H3 divided by the quantity H1 minus H4. And so that was, I got 7% last time, but this will be better.
Yeah, well, I did work net over the heat at the boiler, gave me the same thing, right?
Yeah.
Okay, yeah, then I got 0.3875, which seems like a more typical value.
Right, 388, call it. Yeah, right. That's about what we usually get.
I did this right. I got a reasonable value.
Yeah, I just looked up all the wrong values because I was using megapascals instead of kilopascals. And then the last thing is, so this one we didn't do in number one. So now we're going to figure out the mass flow rate of the cooling water. So now we have to go to think about the condenser as, so okay, here's the condenser. And we have state 2 here and state 3 here. And then we have the cooling water going this way. The one on top here, the way I have it drawn, is the working fluid. And so this is going to be our control volume. So we'll go dE dt is equal to Q dot minus W dot plus, I'm going to throw away all the potential and kinetic energy terms. So we just have M dot for the working fluid times H in minus H exit. I can write that as H2 minus H3.
Well, actually, isn't that the, oh yeah, working fluid, no.
Yeah, and now, and then plus for the cooling water, we have, so this is just going to be H inlet minus H exit. That goes away, that goes away, that goes away. And so we have we can think of this as the mass of the cooling water dot is equal to mass flow rate of the working fluid times the quantity H2 minus H3 divided by H exit minus H inlet of the cooling water. And so the last thing we have to do is just calculate that change in enthalpy for the cooling water. It says that from the inlet to the exit, the cooling water has a temperature change of 18 degrees. And this is a liquid the whole time, so we can calculate the change in enthalpy as the specific heat of the water plus R. No, I'm thinking of an ideal. So C times the change in specific internal, C times the change in temperature plus change in PV. So that's going to be the specific volume times the change in pressure.
Then plus the pressure times the change in volume.
Well, this is water, so there's not going to be any change in volume.
Oh, yeah, but I should say for the whole equation you have that, and then that goes to 0, and then V delta P also goes to 0, just by the incompressible assumption. Or wait. I don't know, I made the leap of that delta P going to 0.
Yeah, well, the enthalpy. The enthalpy is.
Sensor, I know the working fluid we have written is isobaric. Is the
right.
cooling fluid also isobaric?
Right.
We made that assumption.
Right. It seems like that probably is true. We don't know anything about the pressure, so there's no way we could fill that term out. I might have to get back to you on that one, but
let's just assume that was also isobaric.
Okay. Yeah, it makes sense. And so this is 4186 times 18. So that's 75,348. And so now you can calculate the mass flow rate of the cooling water is 120 times whatever we had for these, divided by 75,348. And so what do you get for this?
I got 2,332.1.
1 kilograms per second.
Which I think should be reasonable. It's 120.
Yeah, it's 20 times the mass flow rate of the working fluid.
Yep, which I think your example problem was like 10 times.
Mm-hmm.
So that should be reasonable.
Yeah. Any other questions about that one? So I guess maybe I'll do, so number 5, it gets a little bit different because on number 5, we start using the efficiencies of the isentropic efficiencies of the pump and the turbine. So I guess I'll do that on Tuesday. And remember, when you work on number 5, remember to use the that starting temperature that I gave you today. It's up, yeah, it's updated now on the problems, but it wasn't right before. Okay, that's all. Happy Thanksgiving.
You just list problems directly out of the book, so we can get our. You're never wrong, and we get our.